Hi everyone and welcome to the video. This video is just a review about the first chapter in the Mathematical Methods book, the Year 12 Methods book on functions. So the very first part of the chapter we look at exponential functions. So our most simple exponential function is in the form y equals a to the x. So x and y are the variables, and a is a fixed number. It can be 2 or 3 or 5 or whatever you want. Under these conditions it has to be though. So that's our most simple one. And that graph looks like this. So if this is y and this is x, and all of the graphs have the y-intercept of 1, because no matter what a is, when x is 0, when we're finding the y-intercept, any value of a to the power of 0 is always going to be 1. So that's what this one looks like. And it's representative of what we call the exponential growth function, because as we raise the value of x, a is exponentially increasing. So as you can see, when x is raised, this gets steeper and steeper, this curve here. So we call that exponential growth. So that's the most basic exponential that we have. We can have other exponential functions in this form, the general form. So when we've got more letters involved, it just means it alters this graph basically in different ways. So b, a number that we add or subtract on the end, either raises or lowers the graph. So if b was 1, this graph would be lifted up 1 unit. Every point on the graph would be lifted by 1 unit, and so the whole graph would lift by 1 unit. If b was negative, if it was say negative 4, the graph would lower 4 units. So we say b controls vertical translation. So that's basically just what that means. C controls horizontal translation. So when we change this value of c, it's a similar principle. The graph will either move left or right. So that's what c does. Obviously, if b and c are certain numbers, it will this graph will be translated both vertically and horizontally. So c controls horizontal translation. A controls steepness. So if a was 2, you'd have a graph that would be a certain steepness. If a was 3, it'd be steeper, because a number which is bigger, exponentially growing, is going to yield a graph that looks steeper. It'd be easier to do this by drawing examples, but this is just a basic review, like a rundown. Equation of horizontal asymptote is y equals b. So you've always got horizontal asymptotes with these graphs, these exponential graphs, and they're of this form here. So say you've got y equals 2 by 3x minus 1 plus 4. So this graph would have the horizontal asymptote of y equals 4. So this one is exponential growth, because for a is greater than 1, the function is increasing, and for k is greater than 0, so that's exponential growth. So that is what we've got here, because k is greater than 0 and a is greater than 1. So you're going to have a graph that is exponentially increasing. So it's going to look like that one. So you'd have a graph that looks, it's not going to look exactly like this, but the asymptote is definitely going to be a y equals 4. So that's our horizontal asymptote. And so it's going to look something like that. So yeah, it's basically this graph lifted up 4 units from the x-axis, which is this bit here. So yeah, it affects horizontal translation, and it is also the equation of the it affects vertical translation, and it is also the equation of the horizontal asymptote. Alright? So we call this one the exponential growth model. We call this one the exponential decay model. So in applications for this one, you might be looking at compound interest. For this one, you might be looking at radioactive decay, and we can have a model that's an exponential decay model for that. So if you have one that's like this, where A lies between 0 and 1, so you might have y equals 2 times a third raised to the power of x plus 3. So this one would be an exponential decay model. Also, if you have a negative power here, so if you've got y equals 2 times by 3 to the minus 0.2x, say if you've got one like that, that is also exponential decay, because you can write that as 2 times 1 over 3 to the 0.2x, because this one basically you can write as so whenever you've got a negative there, it's always 1 over that to the positive power. So it is this, but really we can write all of this as 2 times a third to the 0.2x, because 1 to the power of anything is always going to be 1 anyway. So we've got something that looks like this. So whenever you've got k is greater than 0 and times by something to a negative power, you can immediately think, okay, that's decay. And if you've got, say, y equals, I'll just do the reverse just to show you. If you've got that, where that's positive there, that is going to be exponential growth. So these are the main ones really that we're looking at, growth and decay. And then these are the other cases that you can have as well, which we may encounter, or will encounter actually, but these are the most common ones. So with logarithms, that's the next section in the chapter. So you've got a to the x equals b. So this number down here is what we call a base. So this is x equals log of base a, b. So usually we would say that when we're dealing with logs that a is equal to 10. So if we're just given something like log 2, we can just assume that that's log base 10 of 2. Or if we have log of 100, we can assume that that's base 10. And so how you work out logs of base 10 is you can use the calculator, but if you've got a power of 10 sitting here, we can say that that's equal to log 10 squared. And so the logarithm of a number is the number that that we raise the base, so I'll put 10 there, is the number that the power of the base number, if we've got the base number written here in terms of expressed to a power, it is simply the power, so it's 2. So if you've got log of base 10 of a number, if you can make this number a power of 10, you take the power and that's the answer. So these functions here are the reverse of each other. They do the opposite. So we can either raise a number to a power and get an answer, or we can say, after we've gotten the answer, we can say, well, what was the power that this base number here was raised to get that number? And so this is the reverse of what we're doing here. So we're taking a number to a power and getting an answer, and then we want to know what power this number was raised to initially to get that answer over here. So, and then we're back to what x was originally. So basically just think that they do the reverse of each other. They're inverse functions actually. So we've got log laws as well. So log m plus log n is log to the m times n. Log m minus log n is log m over n. N log m equals log m raised to the power of n. So these laws are really useful and we use them all the time. And you would have used them if you've done this part of if you've done the 1b already. And then we come down to natural logarithms. And we use, so this is basically log of base e to the x. That's the natural log because it's of base e. And base e is useful because it's its own derivative. And so it's really handy to use in mathematics, this one, when we're taking derivatives, because the derivative of e to the x is e to the x. So again, they're opposites of each other. Ln is the inverse function of e to the x. So they basically cancel each other out. So if you've got e to the ln of x, you just get x. If you've got ln of e to the x, you get x. So one undoes the other, basically. So you've got the same laws for ln as you do for the other logarithms that we looked at above. The other log laws are still applicable for this because it's just log of base e. So really, with logs, we can have that can be altered. The base can be altered. We can have logs of base 2 or 3 or 8. But if there's no number there, we just assume it's 10. So because they're inverse functions, so we looked at y equals e to the x, y equals a to the x before, actually, I should say. And this is the graph of y equals log ax. So they're inverses of each other, and inverse functions are always reflected in the line y equals x. So one undoes the other. So when you compute a value with this one, and you want to get back to the original value, you use this function here, the inverse. So like pluses and minuses are inverse functions, or times and divide are inverses. If you times something by 2, divide it by 2, you're back to what you had before. It works similarly with this. So as you can see, just by looking at the points, that's 1, comma a. This is a, comma 1. So the coordinates are just swapped around in the brackets. So this is the case where A is greater than 1, where you've got the growth model. And this is the case where A lies between 0 and 1, where you've got the decay model. So in both cases, as you can see, the log graph is the inverse, and it's reflected in this line y equals x. So we use the log function for problem solving with a lot of exponentials when we're working with exponentials, because it's just useful to have that as the inverse function you'll see some worked examples with exponentials where we use logs to find the answers when we're dealing with exponentials. And the last one is trig functions. So this is quite an interesting one, because we've got a unit circle which we use to represent a point P with coordinates cos x sine x, because the unit circle, well, it is a circle, centre 0 and radius 1. That's why it's called a unit circle, because it's got radius 1 unit. And so we get these coordinates here basically by saying, if you remember from year 10, we've got SOHCAHTOA. If you did use this to memorize sine, cos and tan, so if we take out this triangle here, we can see that the hypotenuse is 1, it's a right angled triangle. So if we take the sine value, it'll be sine of x is opposite over hypotenuse, so that's the opposite side there. So that is opposite over 1, which is the hypotenuse. So you just get whatever that opposite side is, that is going to be your sine value, which we can read off of the y-axis there, for that particular angle of x. And same story with the cosine. We can have cosine x is adjacent over 1, because it's adjacent over hypotenuse here, and you've got the adjacent side over 1, which is the hypotenuse, so it just equals the adjacent side. And you'll find as you go around the circle, it's going to be exactly the same, because the hypotenuse of the triangle is always going to be 1, except of course when you get to these points where there's no triangle. So it's just 0, 1 or 1, 0 in those cases. But that's how we derive this here. So we've got exact values of certain angles of x as we go around the unit circle. So these ones are the ones that we use multiples of pi on 6 and pi on 4 as we go around the unit circle. And so I can say, so this is, as we just saw, this is cosine of the angle, sine of the angle, the x-coordinate and y-coordinate. So say we're looking at this one here, where this angle is pi on 3. So that's what these represent. These represent the angles. So this angle here is pi on 3. So cosine of pi on 3 radians is equal to 1/2. Sine of pi on 3 radians is equal to root 3 on 2. And as you can see, we've got the same numbers popping up in all of these angles really as we go around the unit circle. So I'll just erase this so I can show you. So we've got multiples of pi on 4 here. So we can derive these angles of pi on 4 by saying, okay, well, first of all, you've got a full revolution is 2 pi radians. 360 degrees is 2 pi. Because if you look at a circle's circumference, you've got 360 degrees equals 2 pi r. That's the distance around a circle. The circumference is equal to 2 pi r, and that's 360 degrees. Okay, so radians and degrees are different measures. So when we're working in radians on the calculator, we have to go to mode, and instead of degrees, we have to change it to radians, because otherwise we'll get the wrong answers. So 1 radian is actually equal to 360 divided by 2 pi, and that's just rearranging this equation. So back to this, if x is equal to 1 radian, it actually works out that it sweeps 1 radius measure of the circle's circumference. So you'd have which in this case is 1, because we're dealing with the unit circle. So you've got this. So when we're looking at the unit circle and taking the multiples of pi on 4, as you can see, this one is 1 pi on 4, this is pi on 2, so this is going to be 2 pi on 4, excuse my pen. So that's this one, which is 2 pi on 4, which is pi on 2, which makes sense, because if you've got 2 pi in a revolution, this is going to be a quarter of that, which it is. It's a quarter of 2 pi. 3 pi on 4, 4 pi on 4, which is pi. 5 pi on 4, 6 pi on 4, which is equal to root 3 on 2. Sorry, 3 pi on 2. 7 pi on 4, 8 pi on 4. So when we go around the unit circle, we can add multiples of 2 pi to get back to the starting point. So this is 2 pi radians, or we can say it's 0 radians. But yeah, we're back to the start. So that is what we're looking at. And then we've got our multiples of pi on 6. So this is 1 pi on 6, 2 pi on 6, which is pi on 3, 3 pi on 6, which is pi on 2, 4 pi on 6, which is 2 pi on 3, 5 pi on 6, 6 pi on 6, which is pi, 7 pi on 6, 8 pi on 6, which is 4 pi on 3, 9 pi on 6, which is 3 pi over 2, 10 pi on 6, which is 5 pi on 3, 11 pi on 6, and then 12 pi on 6, which we're at 2 pi again. So that's running through the multiples of pi on 6 and pi on 4, and I'm pretty sure in the textbook it's in a table, but you can memorize it by using the unit circle if you want to. So yeah, you've got those. They're all the values that you have to remember. And they basically repeat themselves, but in the 4 quadrants of the unit circle. So this is the first quadrant, second quadrant, third quadrant, and fourth quadrant. Cosine and sine are always positive in the first quadrant. As you can see, these values are both positive. This quadrant, you've got negative cosine, because in the x-axis, or cosine x-axis, this is in the negative zone, so cosine is going to be negative for these values here, and sine is going to be positive in the second quadrant. In the third quadrant, both are negative, as you can see, because we're in the left-hand side of the axes and below the x-axis, so they're all negative that you're going to get for cosine and sine. And then in this fourth region, the fourth quadrant, sine is negative, cosine is positive. So for all of these angles, we can read off the sine and cosine of them here. So the way I like to, if you do want to memorize this, which, look, I would recommend it, it wouldn't hurt. So for each multiple of pi on 6, you've always got a root 3 on 2 and a half. In whichever they're either swapped around or one's positive and one's negative, but the way that you remember it is you visualize the unit circle in your mind. So pi on 6, just think that that's, we'll just basically picture it as being the first one here, where if you can picture it in your mind, it's 1/3 of this first quadrant going up. So just think that the big component of it, which is this bit here, this cosine of x value, the horizontal component, the big component, when it's pi on 6, is going to be this distance here, and that's your root 3 on 2. That's always the bigger one, okay? And then a half is always this smaller one. So that's the y value, and you know it's, sorry, yes, it is the sine x value, the vertical value. So if you can picture it in your mind, that's always going to have the smaller section for the sine and the bigger section for the cosine. And so you've got root 3 on 2.5. Contrasting to that is this pi on 3 or 2 pi on 6, which is a bit further up the circle. So that's this one here. So in this situation, this is the big part. So that's going to be your root 3 on 2, but in this situation, it's going to be the sine value, not the cosine like this one. It's going to be the sine. And then the smaller bit is going to be the half, because that's the smaller part of the triangle. So that makes up the cosine value. And similarly, you can do that with all of these other ones that have the root 3 on 2.5. And you just picture the quadrants in your mind. So you say, okay, 3 pi on 6 is here at the beginning, not at the beginning, but when you've got pi on 2 radians, so that's here. And then 4 pi on 6 is in the second quadrant. The big part is going to be the sine value. The small part is going to be the cosine value. But cosine in the second quadrant is negative, so it's going to be negative a half, and it's going to be positive root 3 on 2. So you can do it in your mind if you memorize the unit circle for all of these ones. And then we've got our general form of our sine graph. Y equals a sine b x minus c plus d. So say we took the most simple one of y equals sine x. So it looks something like this. So this is 0. That is 2 pi. You've got your y-axis, you've got your x-axis in there. So all of these we can derive from the unit circle. Some of the exact values that lie on this graph we can derive from it. So this one is going to be when x is equal to a half. Pi on 2. That's when you're going to have your peak here. At pi, you're going to have the a 0. When sine x is equal to 0, you're going to have x is equal to pi. And then this one is going to be your 3 pi on 2. So this is when the quadrants cross over, actually. So as we can see from above, when x is 0, you've got your cosine value as 1 and your sine value is 0. So this is the graph of sine x. So if y equals sine x, y is going to be 0 when x is 0, because from the unit circle, when x is 0, sine x is 0. So all of these sine values are going to make this graph for one revolution of the graph. So it's a cycle. We say it's one cycle. So one time that we go around the unit circle, it picks up all these values. And it makes sense because in the first quadrant, which is this bit, between 0 and pi on 2, that's the first quadrant, you've got positive sine. In the second quadrant, you've got positive sine. And then once it gets to pi, you start getting negative sine because it's under the x-axis in the unit circle. So those values are going to be negative, and then they're going to be negative still for the fourth quadrant, and then you're back at the start of the unit circle. Hence, we've completed one cycle. So you've got your sine graph looking like that. So if we were to say that that's equal to, if we were to force it to be into that form above, that would be 1 sine 1 x minus 0 plus 0. So we say that A is equal to the amplitude. So the amplitude for this graph is 1 because A is equal to 1. And the amplitude in geometric terms is the distance from a peak to the x-axis, or from a trough to the x-axis. So these dips here, the end of the dip is called a trough, and this is called a peak, which is the maximum term, with the maximum that the graph can take, and this is the minimum here. And that distance from there to the x-axis is going to be 1. And same with this distance, it's going to be 1. So we know that by looking at the A value. So that's always amplitude. Okay. B. We don't say it's the period because it's not the period. It affects the period, we say. Because the period is actually equal to 2 pi on B. And the period is the distance of one cycle. So the period in this case is going to be 2 pi, because from start to finish, when we've completed one cycle, it's gone through 2 pi. So that's the period there. So B is equal to 1 because it agrees with this really, because we can say the period is equal to 2 pi over 1, which is equal to 2 pi. So B is equal to 1, so it's not the period, but it affects the period. And then we've got C is equal to 0, so that's our horizontal translation. And that will just shift the graph left or right, that number C there. So when C is positive, you'll find that you have the graph moving to the right. When C is negative, it will move to the left. So we say that that's the horizontal translation. And D will lift the graph or lower the graph, just like what we saw with the exponential graphs. It's the same thing. And that is also what we say is the equation of the principal axis. So in the other one we said it was the equation of the horizontal asymptote. This time with the trig graphs, it's the equation of the principal axis. So basically, if you've got a graph, pretty bad drawing, but it runs through the center of it, and yeah, you get your peaks and your troughs from this central line. So we call that the principal axis. In this case, where it's 0, it's just the x-axis, the principal axis. Or we can say the principal axis is y equals 0. Technically, it's the line y equals 0. Is the principal axis for y equals sine x. So we can say for this that it is the vertical translation, and that the principal axis is y equals d. So so that's for your sine graphs, and then your cosine graphs, they work in the same way, except they're picking up all of these cosine values of the unit circle. So the graph will look a bit different. It actually looks something like, shouldn't have done that like that. It's going to look something like this instead. So that's what your cosine, if you plotted those values and drew the graph, it would look something like that. But we can also use this general form for cosine. And it's the same. A is the amplitude, B affects the period, C is the horizontal translation, D is the vertical translation. I know that some of the questions ask about when are there zeros in the graphs. So say you had so basically if you had, I'm just trying to think of well, if you've got any equation, so sine of you make it equal to, if you're trying to find the zeros, you make it equal to 0. Yeah, it's hard without a specific question. It'd be easier to explain with a question in front of me to show you. But basically, you're looking at when sine x equals 0. So you make the equation equal to 0, and then you find the zeros, and if you're looking for the exact values, you're going to find them from here. So in a lot of cases, when you're looking for answers, if you get, say, if the angle turns out to be, say it's or if say you get like say you do all your working and then you get the answer sine of x is minus root 3 on 2, okay, so you would look at the circle, or in your table if that's the way that you're doing it, where you've got minus root 3 on 2 for sine, and it'll give you a certain range of um, angle. So it might say find the values between 0 and 2 pi, or 0 and 4 pi, or something like that, for when sine of x equals negative root 3 on 2. So when it equals negative root 3 on 2, you've actually got two solutions, just for going around the first time of the circle, which is these two here, these two solutions. So say they wanted the answers between 0 and 2 pi, for when x is between 0 and 2 pi. Well, you would say that x would then be equal to, what's that one there, 4 pi on 3 and 5 pi on 3. Because that's when sine x is equal to negative root 3 on 2. It'd be easier with an example in front of me. I don't have any examples. But yeah, so I hope that that was a useful summary. And that's it.